This video is on the objective, use algebraic techniques to simplify trigonometric expressions. And this is number 1. So this is the first video on a question related to this particular objective from your Newton Alta homework. So let's take a look. So again, if you're unfamiliar with the topic, hopefully you've read section 9.1 of your OpenStax Algebra and Trigonometry book. Also, you can click on more instruction in the assignment, see the notes, the videos, the examples they have, and see if that'll help. Alright, so what we're asked to do here is, we're considering only the values of alpha for which, 1 divided by secant alpha minus tangent alpha is defined, right? So only values of alpha that actually make this a defined value, not, don't want things to be undefined. So which of the following expressions is equivalent to this? We have 4 options here. Alright, so this is, use algebraic techniques, so, adding fractions together to make a single fraction, simplifying complex fractions, simplifying fractions in general, all that kind of stuff is what they're talking about here. And also, in the midst of all of it, you're going to have to use your identities, right? All the identities that you should have, in your head by now. All the basic identities, right? The reciprocal identities, the quotient identities, the even-odd identities, those Pythagorean identities, and the co-function identities. All of those you should know those. If not, you should have them in front of you, and know when to use them to help you simplify an expression, right? Rewrite it in a way that takes less writing to draw to write out. All right, so I'm going to write this expression on some paper here. So we're asked to simplify, or 1 divided by the secant of alpha minus the tangent of alpha. All right, and as I go through this first video on a question from this objective, I'll write out some little suggestions on the right side here. What I like doing when I simplify trigonometric expressions. So one of these is to write everything in, using some basic identities. Write everything in terms of sines and cosines. Now you don't have to. Again, these are just suggestions. If you see some other way to work out, simplify the expression, do that. But I'm gonna write everything in terms of sine and cosine. Alright, so if I do that here, the numerator is just 1. Nothing to change there, really. And then down here, secant alpha is 1 divided by cosine alpha. So what I'm going to have here is a complex fraction, right? A fraction within a fraction. So we're going to have to simplify that, algebraically in a minute. Then down here, minus, and then tangent of alpha is the sine of alpha divided by the cosine of alpha. Okay. So again, what this is now a complex fraction, right? Fractions within the fraction. All right. Another suggestion I would make is that if you see the sum or difference of 2 terms, 2 fractions here, write them as a single fraction. So put fractions together, adding and subtracting. And remember, when you add and subtract fractions, you need a common denominator. Together, add, subtract to make single fractions or simple fractions. Now, if you look at these two down here, right? If I'm just going to look in the denominator, you see these two fractions already have a common denominator of the cosine of alpha. Right? So I can put these together, and we have still 1 in that big numerator. And then down here I have 1 minus the sine of alpha over the cosine of alpha. All right. Now remember, this is again still a complex fraction, right? Fractions within fractions. So remember, when you divide, that's the same as multiplying by the reciprocal. All right, so 1 over this fraction here is equivalent to the reciprocal of this fraction. All right, or if you multiply the top and bottom here by cosine alpha, you'd have cosine alpha divided by 1 minus the sine of alpha. Okay. All right, so I've rewritten this expression I started with. Now it's a single fraction where everything's in terms of sine and cosine. Now this particular expression is not one of my choices. Not yet, anyway. All right, so I'm going to keep going. All right, I'm going to keep going. Now something else that's going to come into play. Very often it's useful to deal with squares of these trig functions. And in order to have squares be involved, very often you can do this. You can multiply by a conjugate. Multiply by a binomial conjugate. Now hopefully you remember this from algebra. The conjugate of a plus b was a minus b, and the conjugate of a minus b was a plus b. And when you multiplied conjugates, you ended up with a difference of squares. And I'm hoping this looks familiar from some algebra class you've taken. So very often, if a denominator has multiple terms like this, 1 minus sign, I can multiply by the conjugate and see what happens. Now you can't just multiply the denominator by the conjugate. What you do to the denominator, you must also do to the numerator. Okay, so the conjugate of 1 minus the sine of alpha would be 1 plus the sine of alpha. And if I multiply the denominator by 1 plus sine, I have to multiply the numerator by 1 plus sine of alpha as well. And let's see what we get. Now in the numerator, I'm not going to distribute or anything. I'm going to leave things factored. You got the cosine of alpha as one factor times, and then the quantity, 1 plus the sine of alpha. That's in the numerator. And then when you multiply these conjugates, again, you get a difference of squares. You're going to get 1 squared, or 1, and then minus sine squared. Minus the sine of alpha squared. Now, when you involve squares in your expression, those Pythagorean identities could come into play. Remember the Pythagorean identities. Here they are here. Remember, sine squared plus cosine squared equals 1. Well, if that's the case, if sine squared plus cosine squared equals 1, then 1 minus sine squared, like I have in the denominator there, would be equal to cosine squared. Right? All I did was take sine squared plus cosine squared equals 1, and I subtracted sine squared from both sides. Right? It's an equation. You can manipulate it. So I make that replacement, So now I have, cosine alpha times the quantity 1 plus sine alpha in the numerator divided by, and then this 1 minus sine squared in the denominator becomes cosine squared. And now I have some stuff I can cancel. There's a factor of cosine, or that was the whole reason I left it factored, so I could try to simplify the fraction later. I have a factor of cosine in the numerator, and there are two factors of cosine. This is technically cosine times cosine, so I'm just getting rid of one of those, and this is cosine now. It is cosine to the first. And now I have this, 1 plus this. Now all that's left in the numerator, the only factor left is 1 plus the sine of alpha. And the only thing left in the denominator is the cosine of alpha. Alright, still this doesn't look like any of my choices, but we're getting there. Watch. Alright, just watch really quick. Notice now my numerator has multiple terms and the denominator only has a single term. So remember, you could split this up and say this is equivalent to 1 over cosine plus sine over cosine. Right, if I was to split that fraction up, divide each term in the numerator by the denominator. And this is great too, but what's another way to say these? 1 divided by cosine alpha, that's the same as secant alpha, plus, and then sine divided by cosine is tangent. So after all that, this expression is equivalent to, this one I started with, 1 divided by the secant of alpha minus the tangent of alpha is equivalent to the secant of alpha plus the tangent of alpha, and that was this choice here. And that's as simple as that's going to get. That's as little writing as you're going to need to write an equivalent expression to what we started with. Now, what I just did, all these steps I went through, where I wrote everything in terms of sine and cosine, got fractions to be a single fraction, simplified a complex fraction, made it to another, again, a single fraction, multiplied by conjugates. Multiply, if my denominator had multiple terms, I would multiply by the conjugate, see what happens, and use the Pythagorean identity and all that. Simplify, rewrite, like that was a lot of steps. Now, this is all well and good. I did it. I did it correctly. But I'll tell you this right now, and you've seen this before. You saw this in section 9.1 part 1 videos. Very often there's going to be multiple ways to simplify the same expression. Because there are so many different identities, there are going to be multiple different ways you can simplify an expression. So let me show you how to get the same exact thing in another way, a much faster way, and using this conjugate suggestion that I made earlier. All right, so look at the beginning. All right, we have 1 divided by secant alpha minus tangent alpha. Now that suggestion I made where I said, hey, I like writing things in terms of sine and cosine. You don't have to do that. Say I left it this way. And then I notice, hey, my denominator has multiple terms. Maybe I don't want that. So I'm going to multiply by the conjugate here and see what, and get some squares involved. Right now they're to the first power. So I'm going to multiply that denominator by the conjugate, which would be the secant of alpha plus the tangent of alpha. And again, you can't just multiply a fraction, the denominator by something. You also have to multiply the numerator by that same thing. Secant alpha plus tangent alpha. Alright, now the numerator is just 1 times, secant alpha plus tangent alpha. So that's secant alpha plus tangent alpha divided by, and then I multiplied these conjugates here. So I'm going to end up with a difference of squares. Secant squared, secant of alpha squared, minus, and then tangent squared, right? Tangent of alpha. squared. And again, I'm seeing squares. And when you see squares of trig functions, there's a good chance you can use one of those Pythagorean identities to help you simplify. And there was a Pythagorean identity involving tangent and secant. Remember this one, tangent squared plus 1 is equal to secant squared. So if I subtract tangent squared, we're getting this, right? So based on the Pythagorean identities, we can use this fact and make a replacement here. The fact that secant squared alpha minus tangent squared alpha will be equal to 1. Again, all I did was take that Pythagorean identity, 1 plus tangent squared equals secant squared, and subtract tangent squared from both sides. So now I'm left with, the numerator is secant alpha plus tangent alpha, and the denominator is 1. Right? That is replacing that. And there's no need to write divided by 1. And there we go. And this is very simple. Right? That takes a lot less writing to write than the first one. And that's exactly what I got before, secant alpha plus tangent alpha. But with a lot fewer steps, and it really depends on what you're able to see. All right, this kind of stuff takes some practice. Like I said, I personally find people have an easier time working with sines and cosines. So you put make everything, turn everything into sines and cosines. Get singular fractions. Get simple fractions. Do some factoring, cancel some common terms, maybe perhaps multiply by conjugates to get some squares involved, and maybe use those Pythagorean identities, and then simplify the fraction, and then try to rewrite it in a simpler way after that. Now that you have your sines and cosines, maybe you can write things in terms of secant, tangent, cosecant, whatever. But it takes some vision. It takes some recognition. Practice. You're not going to be really good at this the first time through, I promise you, unless you already know your stuff pretty well. But but you saw just now in this video, I did this same. I turned this expression into this expression in 2 different ways, and there's probably others. Okay, so don't be too discouraged if one way you're working with isn't working out. Go back to the beginning and try something else. But you still, you got to use those identities and, some algebra, some basic algebra concepts. How to add fractions, how to simplify fractions, how to simplify complex fractions, multiply by conjugates, and stuff like that. All right, so I'm going to do, of course, other videos on this particular objective, other questions like this, and hopefully this helped you out when you're working on problems related to this objective on your own. And thank you very much for watching.